My name is Vinesh, Kannan.
And I'm Baoshu, Feng.
I'm Haosheng.
We are sharing the work that we did for the International Mathematical Contest in Modeling, advised by Professor Hemanshu Kaul in the Applied Math Department. Our challenge was to design a drone-based disaster response system for Puerto Rico following the tragic Hurricane Maria. The mission was broken into 3 different interconnected components. We were responsible for delivering medical supplies to different hospitals, as well as incorporating into our flight plan coverage of road networks so that we could provide information for on-the-ground operations. All of the supplies for our mission had to fit into 3 international shipping containers, and we developed a box packing algorithm to make sure that everything could fit and determine how long our mission would last. The first component was to develop a flight plan for the delivery of medical supplies. We were given 7 different drones to choose from to make up our fleet, and we modeled the flight capabilities of each drone based on information about their maximum flight time, maximum flight distance, and maximum payload. We incorporated decay of these performance characteristics into our model, so that way the more weight that a drone had to carry, or the longer it had to fly, the worse its performance would get. In order to consider what type of flight plan to use to deliver the supplies, we had to consider over 3,000 different combinations of drones, payloads, and destinations. And this was even when the number of trips per drone was limited to just 2 legs. In order to make this suitable for modeling, we pre-computed the time that it would take each drone to deliver each type of trip. And based on this, we formulated a linear optimization program. The integer linear optimization program had constraints to represent the medical supply requirements of each hospital, and the cost function considered how much time it would take for the drones to deliver the supplies. Based on the solution to our model, we found that we could deliver our supplies to all of the hospitals across the island in 73 minutes. But this was limited by one particular hospital that was very far away from the others. When excluding this hospital, the remaining supplies could be delivered in just 17 minutes. For a form of sensitivity analysis, we saw what would happen if we doubled and quadrupled the amount of demand from the hospitals. Under quadrupled demand, we only needed 2 additional drones. And with the exception of the extra hospital that was far away from the others, we could still deliver most of our supplies in 17 minutes. This shows that our model is at least fairly robust to changes in the demand of the hospitals.
For the second part, we have 2 main challenges to solve. Firstly, based on the mission 1, we have calculated the possibility of medicine supply. A medicine supply is basic one-shot mission, but we still have another mission, which is the surveillance of the road situations. After the disaster, the road situations is unknown, which is necessary to get the information as soon as possible. But based on so what we have done is we firstly abstract the whole road map from Google Map API, which is pretty helpful, and we found there is a main road circle around the whole island, and another one is at the mid of the island. These are the roads we need to survey to detect. So after that, we construct k-means clustering algorithm to decide the surveillance path. But another realistic challenge is that the drones have maximum flight time limit, so we need to find a port for them to charge. So based on that, we do some research, and finally we optimize the last charging part for a continued robust system to detect the road situation. So this is our final result, which is covering 95% of the road, and it's pretty good.
For the last part, we were given a list of drones to pack, as well as medical supplies to pack in the standard shipping containers. Using an algorithm which implements a quadtree data structure that is extended to 3D, we recursively subdivide each container and pack the boxes as we are subdividing the containers. Here is a sample output of the visualization of a packing configuration. One of the conclusions we came to was that we were able to we were able to have enough supplies to last for 365 days. And in the event that the algorithm was given too much items to pack, either because this is a greedy algorithm or the sum of the box's volume exceeds the container's volume, this algorithm will still return a partial solution as well as any boxes that are left unpacked.
Based on all of our modeling, we conclude that we can provide a drone-based disaster response service for Puerto Rico that can last up to a full year. Each day, all of our supplies can be delivered in 73 minutes, and this number is sensitive to the total demand. Even if the demand were quadrupled, we would still be able to deliver the supplies in the same amount of time, with just 2 additional drones. We also used the drones to survey the road networks and found that we can cover 95% of road waypoints across the island with just 10 charging stations. And every single waypoint would get coverage every 40 minutes. We submitted the paper of all of our modeling and results to MCM, the Mathematical Contest and Modeling. And we were really excited to be awarded the rank of meritorious winner, which means that our submission placed in the top 6% of over 14,000 teams from around the globe. We are very grateful to the Applied Math Department at IIT for supporting our love for mathematical modeling and helping us learn with this very interesting challenge.